Okay, so just want to go over one question from the quiz that I thought maybe was the more difficult one. So your quiz might have been different, but this was kind of the general scheme of the question. So a piecewise function, and it was asking if the function is continuous. So what's the first thing you should always write down um, when thinking about continuity? If you try graphing this, it'll be difficult, right? So the thing you want to write down is the definition of continuity, right? So so each of these functions, each are continuous in their own right, right? But we don't know if the whole thing is continuous. But is it continuous together? So where's the only possible point where this might not be continuous? Because each respectively are continuous. Where's the only point where this function collectively may not be continuous? What's the answer? Where may it not be continuous? 3, right. This is the only place where this might not be continuous. Right, there might be something going on at 3, right? It might be like a jump or a hole, we don't know. So that's what we have to figure out. So what would it mean for it to be continuous at 3? Is if this limit is true. So that's why I was very particular about always writing down this limit whenever we have continuity, because in particular for this question, this is really needed. So first of all, what is f of 3? Right, f of 3 is 2. The only function we care about specifically at 3 is this third function. So f of 3 is 2. Now let's think about the limit. What do I need to do to calculate this limit? Right, I need left and right limits because there's different things going on to the left and right. So which function do I look for the left of 3? Correct, yeah. This is to the left. And this is at 3. This is left of 3. So it's left of 3. I look at x squared minus 2. And that answer is what? Is 7. So first of all, right here, you can tell it's not continuous. Not continuous. So, but I believe the question wanted more things, right? So let's calculate the right limit as well. How do you calculate the right limit? Right, I look at the thing that is to the right of 3. No, I didn't miss anything, just going over this question. So yeah, for the quiz, so you kind of you should know roughly what your score is, but that might be plus or minus depending on partial credit, or if I take like a couple points off for incorrect work. So that should be coming like next week. Now the other class had their quiz yesterday, so I can start creating that. Right, so I look at the right of 3, so that's why I look at square root of 52 minus x. And what is that limit? That is also 7, right? This is 52 minus 3, which is radical 49. Which is 7. So what does that tell you about the limit? It does exist. So the limit as x approaches 3 is 7, but f of 3 is 2. So I believe everyone maybe had the same like answer, but maybe a different question. So it should have been f is not continuous at 3, but the limit does exist. And there may have been a couple other statements, like I think another statement may have been like f of 3 exists. I think that may have been the 3 correct answers. But how do you show your work is you really need to say this statement, right? And then prove that analytically. So this would be like a full credit. Like if you graphed, I wouldn't like that as much, just mainly because you can't really graph everything to solve continuity questions. Okay, are there any other questions from the quiz that you'd like to see? I just thought this one may be the more difficult one. Okay, let's continue on with our discussion of derivatives. So, what's this? So last time we talked about, we did some more rules of derivatives. So let's just list those rules so far. So what is the derivative of a constant? A constant function. What is the derivative? 0. Right? And we justified that by saying, right, a constant function never changes. So what is the derivative? It must be 0, because the derivative is a measure of change. We developed a formula of a power function. And remember that? If you have x to a number power, and it has to be x for number power, it can't be anything else. Right. It's n times x to the n minus 1. We had the derivative of a sum. Remember how to find the derivative of a sum? Right, you just take the derivative of each. Right, so it's either notation, you can write this, or this. And I'll use this notation interchangeably, because in certain circumstances, the d dx is more preferable. How about a product? Remember that derivative? So this one is like the mixing. Correct, yeah. I like to write the derivative of f first. That's fine. And then plus g prime f of x. Or ddx of f of x and ddx g of x. Good. Okay, and we had two trig derivatives. What was the derivative of sine? Yeah, the derivative of sine is cosine. And remember what the derivative of cosine was? Negative sine. Good. Yeah, these are things you should memorize. Okay, so that's so far we have these rules, and we'll develop more. One I should add on first, which is it's not too complicated a rule, but it's the derivative of a constant times the function. So we didn't discuss that, but it's not too difficult. So let's think about what that is. So if you have c times f of x, let's see what the derivative is at a. So by the definition of the derivative, it's limit as x approaches a of what? What do I put up in the numerator? Oh yeah, that'd be the difference quotient definition. So that is also true. Limit as h goes to 0, cf of x plus h minus cf of x. That is true. This would be, yeah, but if I'm doing the average average rate of change definition, yes, it would be cf of x minus cf of a. That's fine. Either definition works. I've been liking the average rate of change definition lately, so that's why I've been doing that more. Let's see, can I move this? Okay, good. So yeah, either you can use them interchangeably, but sometimes one might be easier than the other. Okay, good. So how do you simplify this limit? There's an easy way to simplify this. Oh, yeah, sorry, a. Thank you. Yes, you can factor out the c. And why do you want to do that? Is because what's left over is just the derivative of f. So the derivative of c times f of x is just c times the derivative of f of x. So very simple derivative. So let's do it using, so same idea with the difference quotient. You factor out the c, and then you have the definition of the derivative. So that's c f prime of x. Right, so this is using the limit definition to prove, we can call it the constant rule. Something like that. Well, we can prove it one other way. Let's use the product rule. This is a very inefficient way, but it's just nice to see. What is my product here? So I have two functions. I have the constant function c and the constant and the function f of x. So it's a silly way of doing this. Right, yeah. So by the product rule, it'd be d dx of c times f of x plus d dx of f of x times c. So what's d dx of c? Zero, right? That's a constant. So this whole term is zero. And then d dx of f of x is just f prime of x. And then we can put the c over here. So it's a silly way, but I think it's good practice. Okay. Okay, so that we have this new rule here. So we can add that here. That d dx of a constant times a function is equal to c times the derivative of the function. So when is this useful? Well, if you see, if you have like a sum of terms or a complicated expression and there's a constant, you can just take it out and not deal with it. So don't underestimate how useful that is. Okay. Any questions about that? Okay. So let's do a practice problem. I'll go back to the list or to the proof. Okay. So let's do a practice problem. Let's have d dx of x times sine times cosine. So there's three products here, right? But we don't have a triple product rule. We only have a double product rule. Does that mean we need a new formula for product of three functions? Or can we do something to make this easier? Any ideas? Yeah, so how do you propose doing a product of one first? You said product of one first. So, like, how do you want to pair something together? Sure, yeah. So let's take this as one function. Good, and then let's take this as another function. So then you apply the product rule on f and g, right? Even though this is a product of two functions, it's still a function. So you can treat this as one function. So using the product rule, use a product of x sine of x, and then g of x, and then d dx of g of x, or sorry, we have a definition of g of x, cosine, and dx of cosine, and then x sine of x. Okay, so what's the derivative of x sine of x? Or how do I do that derivative? Not the answer, but what do you do? Yeah, this is a product rule again. You have one thing here. You have one thing here. So do it. So dx, and this is in parentheses, of x times sine of x plus d dx of sine of x times x. This is all multiplied by cosine. Right, this whole thing is being multiplied by cosine. And then how do you, what's the derivative of cosine? negative sign. Good. So when I would just combine the signs and put the x out front, this makes negative x sine squared. Okay, then let's do the parentheses. So what's the derivative of x? One, right? It's a line, so the derivative of a line is always its slope. And also you can think of it as the power rule. But I like to think of it as a line because that reminds you what the derivative is. And what's the derivative of sine? Cosine. So I'm going to bring the x outside. On the left, I mean. Okay, now let's distribute in this cosine. So I get sine x cosine x plus x cosine squared, and then minus x sine squared. Okay, can we simplify the solution at all? Well, there's one thing you can do, is if you factor out an x, then you get cosine squared minus sine squared. What is cosine squared minus sine squared? If it were plus sine squared, then it would be 1. Right? Pythagorean identity is cosine squared plus sine squared is 1. But there's another identity for cosine squared minus sine squared. I'll give you a hint. It's a double angle formula for something. Okay. Yeah, another good one to remember. Cosine squared minus sine squared is the double angle formula for cosine. Another thing we could do, may not be necessary, but if we multiply this by 2 over 2, what is 2 sine cosine? Yes, this is the double angle formula for sine. So if you wanted to make it even nicer, you could put it into one fraction. By combining the denominators. So that might be a nice looking derivative. Okay, so does that make sense how to take the derivative of a product of more than 2 functions? So you split it up, right, into 2 functions and then do it again. So there's no need for a product rule of 3 functions because you can always just choose some combination that's 2. So here's a little practice for you. And I really recommend you do this. And actually, this might have been easy. This choice might have been easier. What I'll do was, what if you chose this to be f of x and this to be g of x? So you should get the same thing, right? Because it shouldn't matter. So this might be easier because the derivative of that is very easy. But yeah, you check that and verify that you get the same thing. So it does not matter how you arrange your product, right? It doesn't have to be the first two in the third. It can be just the first and then the last two. That makes sense. What the difference is and how it's not different. After all. Okay. Yeah. So I would try that. Okay. So let's add one more rule to our repertoire. So last time we ended with the motivation of how would you find the derivative of tangent, right? And instead of having to use the limit definition, which you could do, but the angle formulas for tangent are a bit more complicated, maybe it would be better to develop a quotient rule, right? Because sine and cosine have relatively easy derivatives. So if there's a rule for a quotient, then we're in business. So let's develop the quotient rule. So you tell me, how would you find the derivative of a quotient using the limit definition? We don't know the rule yet. There's a lot to type, but you just do the rule. So let's do it at A. So x approaches A. Actually, I think I made a mistake. Yeah, this actually should be using this notation. Okay, so what is the limit of? Yeah, that's eventually going to be the formula, but we need to show why that's true, right? We can't just magically say it, but good, that's good memory. So, of course, we have to say that g of x can't equal 0, because then this thing wouldn't make sense, or g of a wouldn't equal 0. So how would you come up with that formula? Well, you do the function minus the function at a over x minus a. Right, this is the derivative. Okay, so now what? How would you proceed? Any obvious steps? Or obvious first steps? So we've had a quiz on limits, so now you should be experts in limits. So how would you find this limit? Like, what's a strategy? How do you deal with complex fractions? So when I normally do with complex fractions, I usually have to multiply by something, right? Good, yeah, the GCD. What is the GCD of all the fractions here? Good, g of x, g of a. So let's do that. Let's multiply everything by g of x, g of a, and divide by g of x, g of a. So, Sonia, you wrote out the formula. So maybe you can see how the squared comes in, the g of x squared. So what does this become? In the denominator, we have x minus a, g of x, g of a, which yes, that might turn into a squared. In the numerator, we have f of x, g of a, right, because the g of x would cancel, then minus f of a, g of x, right, because then the g of a's would cancel. Everyone agree with that? Okay. So we're going to use a similar trick as we did with the product rule, right? What do we want? We want this term to pop out. And we want this term to pop out. But I don't have those terms here. So what we're going to do is make them. So what I want to do is I want an f of x minus f of a. So let's put it in there. But what else would I need to multiply to isolate, or to make it f of x minus f of a? Right? There's a g of a in the way. So what I would need to do is multiply by g of a. Do you see why this would give me an f of x minus f of a? Because when I factor out the g of a, then I get f of x minus f of a. So now, as we know, you can't just add something and pretend that's okay. What you have to do, if I want to add this term in or subtract this term, f of a, g of a, what would I also need to do? I need to make this not change. Right? I can't just magically put this in there, right? I need to do something else to compensate. What do I need to do to compensate? Well, if I subtract something, that tips the balance. So to make it balance again, right, you need to add it. But you need to add this exact term, right? So you would add f of a, g of a. Okay, so now let's see what this becomes. So the whole point of doing this was to bring in a g of a here, and then in doing so, we have something else that we can factor. So we have g of a, f of x minus f of a. Or let's put the, I like the g on the other side. We have f of x minus f of a, g of a. Then plus, we have f of a, and then g of a minus g of x. Everyone see that? Okay. So what can we do now? So I won't do the whole step, but notice if you split up the fractions, then you have two terms that are the derivative. Do you see that? Well, not quite. But this term is the derivative, right? What's off about this term here? That does not make it quite the derivative that we know. What's off about this? Yeah, the order, the signs are switched. Does that mean we just failed and we can't find the derivative? Or how do I make it to be what I want it? I want the signs to be switched, right? So how can you fix that? How do you make it g of x minus g of a? Right, just multiply by -1. So multiply by -1, or factor by -1. It's probably a better way of saying that. So that's how you get the minus sign in there. So now if I take the limit of both of these, this is the derivative of f, and this is the derivative of g. So we get f prime of a, g of a, and since these are the same denominator, let's bring them back. Then minus f of a, g prime of a. There's still one more limit. It's not too bad, right? There's an x, g of x here, so let's do that limit. So I have f prime of a, g prime of a, minus f of a, g prime of a, over g of a squared. And that's it. That's our formula. Any questions about that? So notice it's similar to the product rule trick. Adding this little extra term here. So yeah, any questions? Okay, so I'm going to just rewrite it. Over g of x squared. Sometimes, I mean, it doesn't matter because multiplication, you can just flip it. But sometimes people like to write it like this. Well, so if you notice, the numerator kind of looks like the product rule, but there's a minus sign. Everyone see that? The numerator kind of looks like the product rule. There's a mixture of derivatives. But the main key is that the derivative of the numerator comes first. So that's one way to memorize the quotient rule, is that it looks like the product rule with a minus sign. It's a product rule with a minus sign, but the derivative of the numerator comes first. So let's just keep in mind. That's not what we got here. The derivative of the numerator comes first. It's fine. I think that should be the derivative of the numerator. So we actually, let's kind of verify it by doing one that we know. So using the power rule, the derivative of x to the negative 1 is negative x to the negative 2. And by the quotient rule, the derivative will be the derivative of 1, which is 0, minus the derivative of the denominator, which is 1, times the numerator, which is 1, divided by the denominator squared. Yeah, so that verifies that's okay. So let's see what happens if we reversed it. The derivative of the denominator first times the numerator minus the derivative of the numerator times the denominator over the denominator squared. That would give not the right answer. Yeah, so it's a derivative of the numerator first. Okay. Got me scared there if I did something wrong. So yeah, is that okay? So this is, yeah. So I like to do that whenever if I ever like forget a rule or think I know what it is, I like to do it on like kind of simple ones to make sure that remembering correctly. So actually, using this, let's do the derivative of tangent. And I always recommend this, especially when starting out. Don't memorize the derivative of tangent, because it's just an extra thing to memorize. I mean, as you do more practice, you'll start to memorize the derivative of tangent. But if you ever forget, then if you know the quotient rule, you don't need to memorize it. Okay, so what is the quotient rule? So one kind of shorthand is you can write as f prime g minus g prime f over g squared. If you don't want to write out all the x's and the dx's. So reading this rule or formula that we just proved, what would the derivative be? Okay, so what is the derivative? So f prime is the derivative of the numerator. So what is the derivative of the numerator? Cosine. So it's cosine, and then times g, which is the derivative of the denominator. Then minus, so now it's the derivative of the denominator. What's the derivative of the denominator? What's the derivative of cosine? Right, minus sine. And then the numerator, which is sine. And this is all divided by the denominator squared. Okay, so that gives us cosine squared plus sine squared, because you have two minuses, over cosine squared. What is the numerator? What is cosine squared plus sine squared? Correct, it's 1. Remember, because it's plus. Yeah, that's when it's minus, it's cosine 2x. And then what's 1 over cosine squared? Can you write that as a different trigonometric function? Like, is it secant or cosecant? Secant, yes. So it's secant squared. So the derivative of tangent. So no need to memorize this because it's just a nice application of the quotient rule. Is secant squared. Actually, when we sketched the derivative of tangent, if you remember, last time we were sketching functions, the derivatives. So secant kind of looks like this. And secant squared is not too much different. So, or that is secant squared. Yeah, it's always positive because it's squared, and this actually kind of looks like secant as well. But yeah, so any questions on using the quotient rule like that? Okay. Okay, let's do actually the other trig functions. Let's do the other tangent function. Okay, what is cotangent again? Okay. Yeah. Let's actually do cosine over sine. Just for the philosophy being that if you forget the derivative of tangent, then you can't use 1 over tangent. So I think cosine and sine are the easier ones to remember. Okay, so now let's take the derivative. So I'll write it out again, but this is a memorize. This is the first day, so you don't need to memorize it right now. All right, so what's the derivative of the numerator? It's negative sine times the denominator is sine minus the derivative of the denominator is cosine, and then the numerator is cosine, divided by the denominator squared. What's the numerator? What's minus sine squared minus cosine squared? Good, it's negative 1. Right, if you factor out a negative, then you get the Pythagorean identity. Okay, and then what is 1 over sine squared, or negative 1 over sine squared? Cosecant, yeah. Okay, so the derivative of cotangent is negative cosecant squared. And again, I really recommend not trying to memorize right now because it's just a nice application of the quotient rule. And it's not like so long, like you probably want to memorize the quotient rule because you probably don't want to do that. Or if you forget the quotient rule, you may not want to. This might be harder to replicate, at least. Okay. Any questions on that application? Okay, let's do one more, or two more. All right, what derivative probably would come next? The other trig functions. Maybe let's do secant. What is secant? One over cosine, yeah. By the way, if some of you know forbidden law right now of chain rule, you could treat this as a chain rule problem. But that is not something we'll do yet. But so right now we can treat this as a quotient rule. Okay, so let's do it. So again, this is the quotient. I honestly think this is easier as a chain rule, which that's just a word right now, but later we'll learn a rule that will actually make this easier. Okay, what's the derivative of 1? 0. Okay, so we don't have to care about g. Then minus g prime is derivative of cosine is negative sine, and times 1 over g squared. Okay, can I simplify this at all? Yeah. You can write this without a denominator. How could you write this without a denominator? I mean, that's a better statement. And without powers, too. To make it more clear what I'm asking for. So you can write this as a product of trig functions with no powers and no denominators. I think there'd be some extra steps there, but that could be. That is true. The denominator can be 1 minus sine squared, but I think it would delay. But here, let's write it like this, and then maybe you'll see it. Do you see now how you can write this as a product of two trig functions? Yeah, so what is it? Right, sine over cosine is tangent. And then what's 1 over cosine? Secant, right. So what is it? It's secant tangent. So that is the derivative of secant. Okay, any questions about that? So it's just a nicer way of presenting the derivative. Okay, let's do another one. dx of cosecant. This is the last trig one that we have. Okay, what is cosecant? 1 over sine. Okay, so what is the derivative? This one time I won't write out the product rule or quotient rule. So it's the derivative of the numerator, which is 0, minus what's the derivative of the denominator? Cosine. Right, and then times 1. So this is negative cosine over sine squared. Okay, what is that? In similar terms like this, how can you write this as a product of two trig functions? Right. So we have a cotangent here, and we have a cosecant here. So it's cotangent, right? Because the cosine is in the numerator. Okay. All right, so let's write out all the trig functions and see if there's like a pattern. So what is the derivative of sine? Is cosine. Good. What is the derivative of cosine? Good, negative sine. What is the derivative of tangent? Secant squared. What is the derivative of cotangent? Negative cosecant squared. What is the derivative of secant? Right, secant tangent. And what is the derivative of cosecant? Right, negative cosecant, cotangent. Okay, anyone see a pattern? So the cos, all the cos are negative, right? And have a sign. Right, you have sine, you have cosecant, which is 1 over sine. Then you have negative, negative, negative. And the not cos have cosine. Cosine, secant is just 1 over cosine, this is 1 over cosine. And they're all positive. All the tans have a secant squared. Or co. Right? They're all co-secant, some sort of secant squared, all the tangents. And all the secants have a secant tangent. Or co. So, one little way of memorizing that. All the co-functions have negative derivatives, and they have an expression of sine in them. And all the ones that are not co have positive derivatives and have some expression of cosine. All the tangent derivatives have some sort of secant squared, either co or not co, and all the secant or cosecant derivatives have a secant tangent or cosecant cotangent. So just a way of memorizing it for yourself. It's one I like to use. Okay, any questions? So now we have all the trig derivatives. Okay. Okay, let's just do quotient rule of like a rational function like this. This will come in handy when we start graphing. So we can use the quotient rule, right? So first you take the derivative of the numerator, multiply by the denominator, minus the derivative of the denominator, multiplied by the numerator, divided by the denominator squared. What's the derivative of x squared minus 4? Derivative of x squared minus 4 is 2x. All right, the derivative of x squared is 2x, and the derivative of 4 is 0. And then what's the derivative of x plus 1? Yeah, just 1. Okay, so that's the derivative. So if you want to expand it out, 2x squared plus 2x minus x squared plus 4. So this is x squared plus 2x plus 4 over x plus 1 squared. Any questions on application of the quotient rule? Okay, so let's step away a little bit from functions and go, or let's talk more geometrically. So remember what the derivative was. The derivative was found by taking secant lines and then bringing the secant lines closer and closer to a point at which we get a tangent line. So one question we might want to ask is, what is the equation of the tangent line? How could you draw the tangent line? And actually, you already know the answer, so don't actually need to say it. But let's see if you remember what equations of lines are. What info do you need for an equation of a line? Anyone tell me anything? I definitely need slope. And what else do you need? Good. Only a point. Right? You don't need the y-intercept. It's good. Do you know what formula of a line that you could create using only a point and a slope? Yeah, point slope form. So what is the point slope form? It's y minus y0 equals mx minus x0. So this is point slope. So what you have is slope intercept. But we won't be using this one. Well, we might put things in this form, but we won't use this. This won't be very helpful. So all we need is the point, or the slope, and some point. Okay, so what are these things? So if this is A, this is f of A. Here's the line, tangent line. You tell me what is the equation of a tangent line? So you have all the info right now. What's the equation of the tangent line? At A. Good, yeah, m is f prime. Right, that's the definition of the derivative. And what's a point you could use? Good, yeah, the only one you really have, AF of A. So how do you find the equation of a tangent line? Well, it's not too interesting, right? You know what all you really need to know is the derivative and what the value is at that point. All right, so let's do some. So again, I don't recommend memorizing this. As long as you know how to find the equation of a line, you don't need to memorize. So you could say the formula is y minus f of A, which I don't recommend memorizing this because there's no need to if you know the equation of a line. So this is the equation of the tangent line at x equals A. And again, I don't recommend you memorizing this. So usually, like in the homework and quiz, they probably want to write it in slope-intercept form. So you'd have to solve for y, but this would be your setup. Okay, let's do an example. So let's do it. Let's just start simple. Y equals x squared at x equals 3. Okay, what's your setup without using a formula? Because, right, who cares about a formula? What's one thing you would need? You see equation of tangent line, and what's the first thing you should think about? Yeah, find derivative, right? Tangent line means probably need the derivative. Yeah, so what's y prime is 2x. Okay, so now how can I use the derivative? Why do we find the derivative? how can I use the derivative to find some information about the line? Is 2x my slope? Well, what does that mean, right? Slope is a number. This is 2x. What does the derivative tell you? So the derivative, right? Oh, you mean f of 3, yeah. Yeah, the derivative is slope of the tangent line at a point. So derivative at a point, slope of the tangent line at a point. Yeah, so you want to find the equation of the tangent line at x equals 3. So you use what the derivative is. It's a function of slopes. So if you plug in 3, you'll get m. Right, so, and what is it? It's 3 times 2, which is 6. Okay, and then what's the other information I need? A and f of a, yeah. So what would that be? Yeah, so it'd be 3 and f of 3, which is, yes, 3 and 9. Okay, good. So now you plug this into your point slope formula. Y minus y0 is equal to mx minus x0. So this is y minus 9 is equal to 6, x minus 3. Questions so far? Okay, so let's put this into slope-intercept form. 6x minus 18. So y is equal to 6x minus 9. So that's this line. And it's believable, right? It's pointing upward, so a positive 6 makes sense. And it looks like it's going to cross the y-axis in the negative half plane, so minus 9 makes sense. Or it's reasonable, at least. Okay. Any questions about that? All right. Let's do another one. Equation of tangent line of tangent at pi over 4. Okay, what do you do? What information do you need? Right, I need the derivative of tangent. Which is what? secant squared, good. So what do I do with the derivative? Right, plug in the point I care about. Does anybody know how you would find secant of pi over 4? What's cosine of pi over 4? Remember those? Pi over 4 is the nice angle, right? Good. Square root 2, too. It's the one where sine and cosine are equal. Okay, what happens if you square that? Get 1 over 2 over 4. Oh, and oh, look, it's 2. So that's why I chose this one. Okay, so that's the derivative. Okay, what else do you need for the derivative, or the equation of a tangent line? First of all, what is 2? In our line, what is 2? The slope, yeah. So m equals 2. Okay, what else do we need for equation of a tangent line? Yeah, we need the y-intercept, but what's an easier approach to the y-intercept? So we can't just find the y-intercept with all the information we have. We need a different piece of information. Right, we need a point, and in particular at pi over 4. Right, think about it. You have a point that you already know. You know, being a tangent line, it must hit pi over 4. You don't know about where else it hits. So there's only one point that you really know immediately, because it has to be at pi over 4 and f of pi over 4. Right? So what's f of pi over 4? What's tangent of pi over 4? So this is your x0, y0. Yep, it's 1. Right, that's why pi over 4 is such a nice angle, because the tangent is 1, because sine and cosine are equal. Okay, so what is the equation? It's y minus 1 is equal to 2 times x minus pi over 4. So y minus 1 is equal to 2x minus pi over 2. Y is equal to 2x minus pi over 2 plus 1. And then if you want, you could say this is 2 minus pi over 2 or something. But like, this is fine. Just combining the fraction. Okay, any questions? Okay. Okay, let's think about other interesting points. And let's do tangent at 0, because something happens at 0 for tangent. Okay. So f prime is secant squared. Okay, what is f prime of 0? What is secant squared of 0? It's 1, right? Because cosine of 0 is equal to 1. Okay, so I need the point 0, f of 0. What is f of 0? What is tangent of 0? 0. So something weird happens at 0. It's just, no, not y equals 0. Y equals x. That's pretty cool about tangent. So if you look at the tangent line at 0, it's just like a diagonal line. There's nothing, no slope to it. It obviously goes through 0. I just think that's interesting. So it kind of flattens out into an identity at 0. Okay. How about sine? That's also kind of something interesting is going on at 0. So if you remember, last time when we talked about like the second derivative, what was special about 0? It was where the derivative was maximal. So let's find the equation of the tangent line. Okay, what's the derivative of sine? Cosine. Okay, what is f prime of 0? One. And then what is 0, f of 0? Not f prime of 0, what's f of 0? 0. Yeah, something to really be careful about, yeah. So make sure derivative versus function. So what's the equation of the tangent line? It's y equals x again. That's interesting. So like tangent and sine kind of look the same around 0. Okay, how about cosine? No, tangent. Equation of tangent line. X equals 0 for the derivative of sine. Okay, and reason why I'm saying this way. So what's the derivative? So I'm looking at cosine now. Negative sine. What's f prime of 0? Zero. I'm looking at sine, right? Sine of 0. And then what's 0 f of 0? Yeah, 0, 1. So what's the equation of the tangent line? That's a 0. It's y equals 1. And why is that not surprising? It's because that's where the peak of the mountain is, right? It's a flat line, and it hits at 0, 1. Okay. Same for, okay, here's a new notation. So when I write a derivative like this, it means the second derivative. Another way to say the second derivative is writing it with 2 ticks. So these are synonymous. F double prime and d squared over dx squared. So we had talked about the second derivative of sine, right? Well, first of all, how do you find the second derivative? Do you remember? Yeah, it's exactly kind of what it sounds like. It's the derivative of the derivative. Right? So what's the derivative of sine of x? It's cosine. And then what's the derivative of cosine? It's negative sine. Questions about that? Okay, so let's do tangent line. Okay, so if this is my function negative sine, what's f prime? So negative sine is now my f of x. Okay, negative cosine. Okay, what's f prime of 0? Negative 1. And now what is my point? Zero, remember, where do you plug it in? You plug it into f of x, not f prime. All right, so this is f of 0. So what's the equation of the tangent line? Is y equals negative x. So this kind of makes sense by the picture. This is negative sine. And then that's the tangent line. Any questions about that one? Okay, let's keep taking derivatives. So this is the third derivative. So as you get past acceleration, you get less and less, physical, right? Maybe the physics terms kind of get more and more obscure. I think I don't remember what the one after acceleration might be torsion or something like that. So jerk, right. Torsion's different. So yeah, I think you do have one for the one after acceleration, which would be the third derivative. I think as you get further on, it gets more and more obscure. Okay, yeah, so, but it's math, so we can be as obscure as we want to be. So to find higher derivatives, if you know all the ones before, then you can always find the one right after. So what was our second derivative of sine? It was negative sine. So what is the next derivative? What's the derivative of negative sine? Negative cosine. Good. Okay, so now let's take this function and find the tangent line at 0. Okay, so what is the derivative of cosine? Negative cosine? Positive sine, yeah. It's negative. And then what is the derivative at 0? 0. What is the point? 0 f of 0? Again, f of 0, not f prime of 0. Negative 1, yeah. So I think that's always the biggest mistake that people make with tangent lines is remember that you plug into the original function when you find the point. So what's the equation of the tangent line? Negative 1, yeah. Okay, why is that not surprising? It's because if you graph negative cosine, remember the negative just means it's a x-axis reflection. So you're at a valley point. Okay. So maybe you can see where I'm going. Let's take the next derivative. So we just found the third derivative of sine. It was negative cosine. So what is the fourth derivative of sine? By the way, this is just a symbol. I just want to make that clear. This is just a symbol. So you can't like cancel the d's out. So just don't try doing that. It's just a symbol. So don't treat it very religiously. Good, positive sign. Okay. Tangent line at x equals 0. Wait a minute. Didn't we do this one already? Did it already. Okay. What do you think the fifth derivative of sine is? What was the fourth derivative of sine? It was sine. So what's the fifth derivative? Cosine. What's the 17th derivative of sine? Okay, so if you see the pattern, yeah, so what is the pattern? You think it's cosine? I agree. Yeah, so how do you know it's cosine? Yeah, it repeats every 4. So do you know how to calculate it? Right. So 17 is equal to 16 plus 1. Another thing that you're doing is that when you divide by 4, what do you get? You get 4, 16, you get 16 remainder 1. So the remainder divided by 4 gives the derivative. Oh, is that the symbol? Percent sign? Oh, okay. Yeah, so I do it 17 mod 4. 17. I don't recognize that symbol. That's cool. Okay, yeah, so let's do D, what's a fun one? 173. Okay, so you know it repeats every 4 derivatives. So let's divide 4 into 173. Okay, how do you do long division again? What do you divide? How many times does 4 go into 17? 4 times. 1. How many times does 4 go into 13? Is that 3 times? So I have remainder 1. So that means the derivative is also cosine. That makes sense? So this one was cosine. So, okay, yeah, questions about that? Okay, let's do the same for cosine. Let's do a different number. Let's do 214. Okay, do we have to do a whole other thing for cosine? And why or why not? No. Right, cosine already appears in the cycle for sine. Right? So, oops. What is it the same as? Well, same as doing one less derivative. Sorry, one more derivative. Good, yeah. One more derivative of sine. Right? Because what is this? It's d214 over dx215 of d dx sine x. Right. So, okay, so now let's do it on 215. Okay, so 4 goes in 21 5 times. That goes in 3 times. That's remainder 2. Okay, so which one is remainder 2? It's negative sine. Okay, so just an interesting fact about sine and cosine, right? They have this nice periodic nature in their derivatives as well. But it turns out the same cannot be said for tangent. Tangent doesn't have these nice repeating derivatives, right? Tangent's also periodic, but its derivatives don't behave as nice. If we go back to the derivative of tangent, did we? Yeah, we did. Oh yeah, where's the chart? Yeah, secant squared. So if you think about doing the derivative again for secant squared, it's going to get kind of complicated. So there's no nice periodic nature for tangent derivatives, but there is for sine and cosine. All right, I think we're done now, right? 7:20. Okay, I'm going to stop recording.